They react with acid paper they're not sour, they're not being system. They react more than those H2. You get well, give me the last one. They sort of take.
Okay. I'm going to draw cards today. Because why not? What? You might have to talk? Do you know what? If you feel uncomfortable for talking for any reason, you can just say pass. Okay? No pressure. Like, if you're just like, I'm not in the mood today, that's okay. I'm all right with that. But I'm just going to call names because I need this lesson to move along. Yes? Because we spend a lot of time going, anyone? Bueller? Okay. So, any property of an acid or a base, Jaden? Acids start with hydrogen. I'm going to put that over here. Because that's not a property. That is how you can recognize one. Does that make sense? Okay, so not a property. Property is like a characteristic. That's not like, so a characteristic would either be a physical property or a chemical property. That is how you might describe an acid or recognize an acid. What is a property of an acid or a base, Victoria? Release H plus ions in water. That is a definition of an acid. That is a specific type of definition of an acid. It is an... Anyone remember what that name was? Okay, so you remember it starts like a pirate. Arr. Arr. And then we have the chicken. Hen. Yes. Yes? So we have a pirate chicken and then IUS. Okay? Arrhenius. It's not pronounced Arrhenius, it's pronounced Arrhenius. Okay, so that is a substance that releases hydrogen in water, and this is a definition. What is the Arrhenius definition of a base? Sorry? Yeah, a substance that releases hydroxide in water. Okay, and we're going to go back to our properties of acids and bases. Tiago. Any property. Bases are slippery, yes. Okay. Acids are sour. Juan. Any property of an acid or a base?
Acids react with bases.
React with bases. Sasha. One is corrosive. So acids react with some type of things to produce metals. Yes. So this is kind of in the corrosive category. And do you guys know what they produce? They produce hydrogen gas. Okay. And there's a reason I put that one with slippery, because there's no comparative one with slippery. There's no like analogous property. Whereas I can say that acids taste sour and bases taste bitter. So those two go together, right? And I can say that acids react with bases, and I can say that bases react with acids. And those two go together. Katie, got another one? Dissociate in water? It is. I'm not going to put it on our list, though. Oh, it is a property, though. You're absolutely correct. Okay. Yes? Low pH, yes. So we're actually going to go with 6 properties. Because pH is one that's not on this list, because in theory, you haven't learned pH yet. Okay. pH, what can we say about the pH? pH is, sorry? Below 7. And I'm going to put at 25 degrees Celsius, because that number changes if you're not at 25 degrees Celsius. So correspondingly, bases, their pH is greater than 7 at 25 degrees Celsius. Now we're kind of scraping the end here. We got what? How many more? 1, 2, 3, 4. So we need 5 and 6. Sylvia, do you know one? Okay, that's fair. Anybody have any more? Yeah, John. Acids turn litmus paper red. And what do bases do? Everyone? They turn litmus. What color? Blue. What are we missing? Oh, yeah. So we have all the ones that are like sort of opposites of each other, right? So that's the sour and bitter. I mean, they're not necessarily opposites, but they're contrasting, right? We've got sour and bitter. We've got react with bases, react with acids, pH less than 7, pH greater than 7, turn litmus red, turn litmus blue. There is one that they have in common with each other. Yes? They are corrosive. I don't like the word corrosive, though, because it's just so vague. Do you know what I mean? Like, it's like, what are they corroding? Are they actually talking about like oxidation or whatever? So we're just going to leave that one out. You guys were to have written this out last night, weren't you? Yes. They conduct electricity. Yeah. Okay, so those are the ones that's the one where they are the same. And then we have the two that are completely unrelated to one another. We have the reacting with metals. And then we have slippery, which has nothing to do with reacting with metals. Okay. So you've now learned about Arrhenius acids and bases and some properties of acids and bases. And this evening, that was section 4.1a. This evening, you are going to go home and you are going to learn section 4.1b, because there's a video that goes along with it. And that's going to be about Bronsted-Lowry acids and bases. So you've learned about the Arrhenius definitions. You are going to learn about the Bronsted-Lowry definitions. But we, as a class, are going to learn about them only peripherally today. But we're going to focus instead on section 4.2, which is all about pH. We're on page 66. You will get a little preview of Bronsted-Lowry acids before you go home tonight and learn about them for real. So we are looking at the pH and the pOH scales. We'll learn about pOH, but it's really similar to pH. And you'll notice that it goes from 0 to 14, except that it can actually go, it can go above 14, and it can go negative. And what do we know about pH 7? pH 7 is neutral. However, I'm going to put a caveat on that. Do you guys know what a caveat is? Caveat's kind of like a warning or a like an exception-y kind of a thing. It's like, watch out for this because it's different. Okay. So there's an exception to this because this is only true at 25 degrees Celsius. However, if you're close to 25 degrees Celsius, it's going to be close enough. So if we're working at room temperature and room temperature is 20 degrees, we're not going to be like, oh, pH is not 7, neutral pH is not 7 anymore. It's going to be close enough. Okay? Now, as hydrogen ion gets higher, so as hydrogen gets higher, the pH gets lower. Okay, so you have to remember that they go opposite directions of one another. So up here, we would have, in this area, we would have our highest concentration of hydrogen at this end of the scale. And we would have our lowest concentration of hydrogen at this end of the scale. Each number on the pH scale represents a 10 times change. So each number is a 10 times change. So let's look, for example, if we go from pH 7 to pH 6, hydrogen ion concentration has increased by a factor of 10. Okay, so it's 10 times bigger. Because remember, as the pH number gets smaller, the concentration of hydrogen gets bigger. Okay? As we go, say, from 5 to 3, we are now moving 1, 2 units over. So instead of 3 having 10 times the concentration of pH 5, pH 3 would have 100, which is 10 to the 2. Yeah? Times bigger. Now, what if we go the other way? If we go from pH 8 to pH 11, is hydrogen getting higher or lower? It's getting lower, and we are moving by 1, 2, 3 units. So how much lower is the hydrogen ion concentration? Pardon me? 10 to the 3 times lower. Okay, so you should get decent at playing with those whole numbers in your head. Now, what scale, what kind of function represents, or what kind of function are you using when you always have 10 times changes? Does anyone know? Those are logs, okay? So the pH is a logarithmic scale, okay? And if you remember, if you take the log of 10 to the 3, what do you get? Three. Yeah? If you take the log of 10 to the negative 6, you get negative 6. That's how logs work. Okay? So whatever this number is here is that number there. So when you're working with whole numbers, those two numbers are the same. Okay? And I'm going to give you the formula for pH right now. pH is equal to, and wouldn't it be nice if it were just the log of the hydrogen, but it is actually the negative of the log of the concentration of hydrogen. And the reason is that most of the time our concentrations will be less than 1. So we end up with mostly negative exponents. And isn't it nicer just to say pH is 6 rather than pH is negative 6 and having a scale that goes from negative 14 to 0? You know what I mean? So they just made it positive by tacking that little negative sign on the front there. Okay? This is a formula that you must memorize. They probably give it to you on AP. Let's check. Yep. They give you pH. And you'll be like, hey, where's the hydrogen? We got this H3O plus thing. We'll talk about that today too. Okay, don't worry. We'll get there. All of these things will become clear with time. Okay. All right. Now, in order to have a very low pH, and if you have a very low pH, what sort of a thing do you have? You have something that is very acidic. In other words, it has a very high what? Concentration of H plus ions, okay? So in order to get a very high concentration of hydrogen, you either need to have a strong acid. What makes an acid strong? It dissociates completely, okay? Strong acids dissociate completely. And basically, if you've got a strong acid, you can have fairly low concentrations of that acid and you'll still end up with a decent amount of hydrogen. Okay, so let's say, for example, we have HCl. Is HCl a strong acid or a weak acid? Strong. So if we had the concentration of HCl equal to 0.1 molar, what would be the concentration of the hydrogen ion? .1 molar. Okay, because what's happening is we have our HCl, and it dissociates completely, one-way arrow, into H plus and Cl minus, and we can draw ourselves not a rice table this time, but we can draw a Ricfa table, because we still have the reaction, we still have our initial concentration, which this one is 0.1, this is 0, this is 0. We still have a change in concentration. These are all 1 to 1 to 1. This gets all used up. And it's not an equilibrium concentration anymore because there is no equilibrium. It is a go to completion situation. So this is final. And I've not come up with a better name than a Ricfa table. I'm sorry. If you can think of one, please let me know. I would be happy to take such a clunky term out of my vernacular. All right, but this is going to go up by 0.1, this is going to go up by 0.1, and so this is going to be 0.1, and it's going to be 0.1. You do not need to show all of that. You can just be like, I know this is a strong acid, and so it all turns into the hydrogen ion. Yes? But I'm introducing you to the Ricfa table because there will be, I think, some in tonight's or tomorrow's homework. Okay, so you'll have seen it before. So, any strong acid will generally end up with a lot of hydrogen. And we got a little picture here of our strong HCl, and it, at most concentrations, we get a ton of hydrogen ions. Yes? You would have to dilute it like a lot to get a low hydrogen concentration. Yes? Okay. Because it dissociates completely. There you go. Now, if we have carbonic acid, which is a weak acid, and that is H2CO3, it dissociates into, yes?
Do bases have hydrogen?
Bases have, they either have hydroxide ions, which makes them an Arrhenius base, then they can release them, or what they will do is they will take, I'll explain this in a moment. Can I explain it in a moment? Okay, because I just want to finish this and then we'll be like, okay, we're going to go there. All right? Because it goes into the Bronsted-Lowry, which again, we're going to get a little preview of, and then you're going to go home and learn about in depth tonight. Okay? So this dissociates. It's really only the first hydrogen that dissociates to any great extent. The second one mostly stays on. even if you have a very concentrated solution, it's weak. So few acid particles would ionize. So if we look at this, are there many ionized particles? No. Okay? Only a little, a tiny bit. So in order for a weak acid to have a low pH, in order for a weak acid to have a high hydrogen concentration, you would actually have to make it very, very concentrated. Okay? And if we're like, what do I mean by a tiny bit? Well, let's go look at our data booklet. Okay, we're going to look at our data booklet on page 5. Nope, 6. So if you want to grab your data booklet. Page 6. You will be using your data booklet very frequently for the next 1, 2, 3, 4 units. So just at the beginning of class, haul out your data booklet because I will refer to it almost daily. Okay? So here we have our names of our acids on the left, and here is carbonic acid. It is H2CO3. You can see we have an equilibrium arrow here. It goes back and forth. And this number over on the right, that is the KEQ for that dissociation. We call that a Ka because it is a K for an acid. Okay? That's 10 to the negative 7. Big number or small number? That's a small number. How much hydrogen are you getting out of this thing? Hardly anything. Even if you made this very concentrated, it would be hard to get a low pH, like a really low pH. Does that make sense? Because your concentration would be like, I don't know, like 10 to the negative 3 or something like that. Like, yeah. All right. So, going back here. So the upshot of this is that at any given concentration, a strong acid has a lower pH than a weak acid. Is good? Okay. All right. Now we're going to go through this here. This should say 3. I need to fix this. All right, let's fill in this table together. As pH increases, what happens to hydrogen ion concentration? It decreases. As pH decreases, hydrogen ion concentration increases. Now, in my last block, we got into some sort of question, and I can't remember what it was, but we ended up taking a little preview at Bronsted-Lowry acids. So if you've got some paper you want to take notes on, that's great. If you want to just sort of absorb it, that's also fine. Okay, so we would have in water at any given time. Oh yeah, the question was, so if our hydrogen ion concentration is at 0, does that mean it is neutral? Okay, that was the question. And the answer is no. And the reason is that if you have water, you have hydrogen ions. If you have water, you have hydroxide ions. And I'm going to show you why. If you take a water, H2O, and you put it together with another water, H2O, then one of them can act as a Bronsted-Lowry acid. So this is as opposed to an Arrhenius acid, and a Bronsted-Lowry acid is a proton donor. Now, what the heck do we mean by a proton donor? Let's think about a hydrogen ion, or sorry, a hydrogen atom. What is in the center of a hydrogen atom? One proton. What's around the outside of a hydrogen atom? One electron. So if we have an H+ ion, what do we have? We have one proton. So when we say a proton, what we really mean is H+. Okay? So in Chemistry 12 and from now on, if you hear proton, we're mostly referring to the hydrogen ion rather than referring to, because we're not really looking at the nuclei of things in this course, of atoms in this course. Okay. Now, what does water contain? Water contains hydrogens, yes? So water could be a proton donor. Now, what if we had a Bronsted? And if you want to be really fancy, you can put the little umlaut over the O, okay? The Bronsted-Lowry base. What do you think a Bronsted-Lowry base is? It's not a proton donor, it's a proton receiver. Okay, I'm going to use the word acceptor because that is the more commonly used language, but receiver also works. If you said proton receiver, you would be fine. Okay, proton acceptor. So let us take our water and we'll write it now as HOH plus HOH and what's going to happen is we're going to take this hydrogen here and we're going to donate it to this water over here. So we're going to take our H+ and it's going to move from one water to the other water. What will we be left with from the first water? Hydroxide. And what are bases? They're things that release hydroxide. Look at that. Released hydroxide. Oh my gosh. Okay. And what would we end up with our other species? What would it be? It wouldn't be H2O anymore. It would be H3O. And because we gained an H, not just an H, but an H+, it would be H3O plus. Okay? And I don't know why I drew a one-way arrow, because this is not a one-way arrow. This is an equilibrium. So anytime you have water, you will always have hydroxide, and you will always have, this ion here is called hydronium. And it is the reality of the hydrogen ion. There is actually no such thing as little H plus ions floating around in water. They don't do that. They grab onto a water and they form H3O plus, okay? So we use the terms hydrogen ion and hydronium ion interchangeably almost, yes? Because hydrogen ion is like shorthand form. It's like how you write it short, but in reality, what you've got is you've got H3O plus. And if this is all like what's happening, don't worry. Mr. Kolger will take care of you tonight and we'll show you on the video. Okay, it's a 13-minute video. All right. So we have this, there we go. And because this is an equilibrium, we could write a KQ. And that's going to be equal to the concentration of hydroxide times the concentration of hydronium, which we can say is the same as H plus and this is going to get us back to where we were over here. As hydrogen ion concentration increases, so let's say we add an acid to water, okay? If we add an acid to water, and remember this guy here is H plus, hydronium ion concentration would increase, hydrogen ion concentration would increase. What would happen to this equilibrium? It will shift to the left. And as it shifts to the left, what happens to the hydroxide ion concentration? It decreases because we're using it up. Okay? So when you add hydrogen, the water equilibrium will shift to the left. It will use up hydroxide and hydroxide goes down. So anytime you have hydrogen increasing, hydroxide will decrease. Conversely, if we were to drop the hydrogen, the system would shift to the right. Okay, let's go back here. If we were to drop hydrogen, the system would shift to the right. And what would happen to the concentration of hydroxide? It would increase. So if hydrogen ion decreases, then hydroxide decreases. Increases. Thank you. Oh my God. Just giving you wrong information left, right, and center. Okay. pH is a logarithmic scale. So if pH doubles, does hydrogen double or does it not double? It does not. Okay, you'd have to do some math around that to see what actually happened to it, okay? It would depend on what numbers you started with, how much it changes by. But what we do know is that for every change in unit of the pH, the hydrogen ion changes by a factor of 10. So, if the pH of a solution is increased from 2 to 4, what happens to the hydrogen ion concentration? Tell your partner. When pH increases, what happens to hydrogen? Increase or decrease? Decreases. And in this case, it decreases by a factor of 100. Now, it's wonderful to be able to do that in your head. If you were ever asked to prove it, you could prove it by saying, well, if pH is 2, then hydrogen ion concentration would be 10 to the negative 2. If pH is 4, hydrogen ion concentration is 10 to the negative 4. And if you don't believe me on that, do you remember our pH formula? pH is the negative of the log of the hydrogen, right? And if hydrogen is 10 to the negative 2, that's going to be the negative log of 10 to the negative 2. And the log of 10 to the negative 2 is negative 2, right? And then we got that negative in front. So that then becomes positive 2. So if you are dealing with whole numbers, pH and hydrogen ion concentration are easy to go back and forth between. Okay? The exponent becomes the pH, except for you have to make it negative. And if you're going from pH to hydrogen, it becomes the exponent, and you have to, again, change the sign. So as we go from pH 2 to pH 4, we go from 0.01 molar to 0.0001 molar, which is divided by 100. And the difference between these two is 2, yes? So our factor is 10 to the 2. So 4 minus 2 is 2. Those are our exponents. Or you can just do it in your head. If the pH of a solution has decreased from 7 to 4, what has happened to the hydrogen ion concentration? Hydrogen ion has increased by a factor of, so we say 7 minus 4 is 3. And it doesn't matter whether you go 4 minus negative 2, you just find the difference, just the overall difference. Because when you're talking about a factor, you can say it increased by a factor of 1,000 or it decreased by a factor of 1,000. Yes? So it has increased by a factor of 10 to the 3. Another scale that is related to the pH scale is the pOH scale. I would like you to see if you think you can write the formula for calculating pOH. pOH is the negative log of the concentration of OH. And again, you need to memorize that. Not because you need to memorize it for AP, but you do need to memorize it for the regular test. And I will say, having dealt with a few questions during the equilibrium test and having read a few answers for the equilibrium test, you guys need to memorize that all tell your partner what those three things are. If you and your partner don't know, go find someone else who does, because I'm going to draw some cards and people are going to answer me. So if you don't know, go find someone who does. Okay, Aditya, what is one type of salts that are always soluble? Did you three not come up with anything? Then why did you not go visit somebody else? Did I not say, I'm going to call a card, go visit someone else if you don't know? We're going to do this again. Everybody who doesn't know is going to go visit around the room until they find somebody who knows. Oh, we got a nitrate. Okay, yes. All nitrate salts are soluble. Do you know them now and you just didn't know what I was talking about? Yeah? Do you want to give me another one? All the alkali salts are soluble. And the third one, she's writing a test. Not here. Not here. John, ammonium. Okay, very nice. Thank you. Okay. So memorize those. Memorize them. Memorize that formula. So if we look at this scale, and remember this scale is at what temperature? This is at 25 degrees Celsius. When we have a pH of 0, hydrogen ion concentration is 1 molar. And remember, that actually means that we have 10 to the 0, right? That 0, 10 to the 0 gives us 1. If we have pH of 1, hydrogen is 10 to the -1. If we have a pH of 2, hydrogen ion concentration is 10 to the -2. And so on and so forth, all the way up until we get to 14, which is 10 to the -14. Is it possible to have a concentration of hydrogen equal to 10 to the -15? Is that possible? Sure, which is why this scale can go past 14. It doesn't happen a lot because that's a really low concentration, but it can happen, okay? And you could get a pH of 16, again, really, really small hydrogen concentration. If we go back the other way, is it possible for us to have, and I kind of ran out of room here, so we're going to have, sorry. Is it possible to have a pH of -1? What would that mean about our hydrogen ion concentration? It would be 10 to the 1, which is 10 molar. Yeah? And the reason that we don't have very many pHs that are negative is because most acids kind of max out in how much can be dissolved in water, and an acid has to be dissolved in water. Maximum concentration of nitric acid is, I think, 12 molar. I think sulfuric acid is 16 molar, but I could be wrong. But like they're not that big, that more than 10, not much more than 10, right? So, and concentrated acids, we don't work with them very much because for certain reasons, like if you get them on you, I got concentrated nitric acid on my thumb once, it turned yellow and a whole chunk of skin fell off. Very exciting, super fun. Okay. So that is our pH scale, but remember, as your hydrogen ion concentration, if it is larger, on this side, H plus is large. What do we know about hydroxide? Concentration of hydroxide is small. Yes? And now we're going to play with math a little bit. I'm kind of excited about this part, so bear with me. Okay. Where did we get to? Here we are. Okay. So we know that this KEQ for this equation here. I'll do that. Yes. These are liquid. If you have H2O, what? H2O cannot be aqueous because water dissolved in water doesn't make any sense, right? Like, because well, here's the thing. They do dissociate, but only a really small amount, okay? Because the KEQ for this thing, it actually has its own special name. It is called KW because it is the dissociation of water. Yes, it's got its own little name. And normally we write the hydronium ion first and the hydroxide ion second, but it doesn't matter. You could write it the other way, yes? And the value of this is, and actually if you don't know, if you ever forget this value for KW, it is in your data booklet because let's look at this. We have, down at the bottom, before the gray zone, we have water, yes? And this particular one shows water dissociating, but remember hydrogen could be hydronium, so it's basically the same thing, right? And it gives you the value, and the value for that is very, very small. Well, it's small, but apparently it's not very small because it's not in that little area down at the bottom. Okay, it is 10 to the negative 14. That is the K value for the dissociation of water. So it dissociates, but only a little tiny bit. Yeah? So this is equal to 10 to the 1 times 10 to the negative 14. And now what we're going to do is we're going to take a look at the dissociation of water or the ionization of water. And we're going to make a rice table. Look at this. If it starts completely dissociated or undissociated, then these are both going to go up by the same amount, yes. And that gives us X and X. So this is pure water. And I should mention that this is the kW value at 25 degrees Celsius. So if we were to then put our X's in there, so our kW would equal X squared would equal 1 times 10 to the negative 14, then what does X equal? One times 10 to the negative 7. And that means that our concentration of H3O plus, which is the same as concentration of H plus, because H plus is really just a shortcut way of writing H3O plus, that is 1 times 10 to the negative 7 molar. What's the pH? What's the log of 1 times 10 to the negative 7? Negative 7. So we have negative 7. So that equals 7. So do you remember? Pure water is neutral, yes? Pure water is neutral. And when we solve for hydrogen ion concentration, we get 1 times 10 to the negative 7, and the pH is 7. But that depends upon kW being 1 times 10 to the negative 14. What do we know that happens to K values when we change the temperature? K changes when we change the temperature. So let's just say at a particular temperature, if kW at a different temperature was equal to 1 times 10 to the negative 16, what would neutral pH be? Right? Neutral pH at 25 degrees Celsius is 7. And that's because kW is 1 times 10 to the negative 14. If we take the root of that, we get 1 times 10 to the negative 7. And that means that if we take our pH, that 7 becomes that 7. So that's why it's pH 7. What would the neutral pH be if we had our kW as 1 times 10 to the negative 16? It would be 8. So neutral pH would be 8. So pH 7 would be acidic at that other temperature, and you wouldn't become basic until you got over pH 8. Yes? Water is always neutral. If you have not added acid, if you have not added base, water is neutral. The pH scale depends on the temperature of water. Yeah. The neutral point depends on the temperature of water. Now, like I said, is it enough that you know, doing it at our room temperature as opposed to 25 degrees Celsius is going to make any significant change in it? No. But you should know that it can change I mean, having a neutral pH of 8 is like actually quite off the charts. Do you know what I mean? Like, we're not talking factors that big, but we'll look at some real numbers a little bit later. Okay? So yeah, the pH scale depends upon the temperature. Yes. pHs are not always whole numbers. We're playing with whole numbers right now because it makes our lives easy, and I don't want everybody, like, you know, hauling out their calculator all the time. Okay? We will play with numbers next day. Okay, so now here's a question. If the concentration of H plus was 0.1 molar, because say we had 0.1 molar, brain, 0.1 molar HCl, there we go. Took a while. Okay, if H plus was 0.1 molar, which is 10 to the negative 1 molar, what would the concentration of OH minus be? What would it be? 10 to the negative 13. So if you've got whole numbers, those two whole numbers are going to add up to negative 14. Yes? If you got whole numbers for those. And if you had, let's say if you had, here's fun. If pH is equal to 8, what is pOH equal to? 6. Yeah? And if you're like, wow, this was too much all at once, don't worry. We're going to actually go through like lots of real-time examples tomorrow. This is just getting you to make your brain do it quickly and easily. Do you know what I mean? Like, just sort of intuitively grasping it. Because we got formulas for all of these things, right? We can be like, okay, if I give you any value for hydronium, you can calculate the value for hydroxide because you know those two things multiply to give you 10 to the negative 14. If I give you any value of pH or pOH, you can calculate the other one because pH plus pOH always equals 14 unless you're not at 25 degrees Celsius. Yeah? In which case it would be something different. But yes. Okay, and I think that is as far as, this is further than I got with my other class because we had the great Canadian shakeout and we were under tables and going outside and all kinds of things. So I think we will leave it there. Your homework is 4.1b. And at the end of 4.1b, which is on page 12, there is some Hebden. There is a question and some Hebden stuff. So you are going to watch the video, fill in the blanks. On page 12, it tells you what Hebden to read and asks a question. And we are super close to being done this unit. Because 4.1 C, D, and E, no, C and D are about strong acids and strong bases, which we know about already. 4.1D is weak acids, which we know already. There is more to it than that, but we've shockingly covered an outrageous amount of what's in this unit. It is a short unit, okay? Whew. Hello. Yeah.
This equation.
Yeah.
Like you got
No.
even if there's two.
Are they two liquids or is it just one liquid?
Well, it's two of the same.
So can they dilute one another and change the concentration of each other?
So that's why.
Yeah. You could also write this as 2H. Yeah. Good question. The question was, these guys are liquids. They don't count as two different liquids because it's the same liquid, so it does not, they do not get included in the KEQ. Okay. You could also just write this as 2H2O instead if you wanted to. Okay. Tomorrow we will formalize all of the little calculations.